All right, I'm redoing some stuff, but this is not really cleaned up. But essentially, where I want to pick up from last time we talked is there are two potential interpretations that. So if you remember, what over the last few times, what we did was we looked at some existing syntactic structures. We were only focusing on the syntactic structures in the collections, not looking at the modal stuff, because the modal stuff is pretty well understood. But we were looking at the syntactic structures in the collections and just showing how there's a crisp, clear interpretation, starting from a syntactic structure and a structure for a collection, how we generate the corresponding type structures. And then now what we want to do is give an interpretation of what it means to for a term to be typed as a member of this type structure. And there are effectively two possible interpretations. One is that we're asking a model theoretically if M is a model for the property, so it's a witness of the property. And the other is proof theoretic. So we're asking is, can we prove M satisfies the property? So can we construct a proof tree? So I want to look, briefly at what modeling means, and then indicate what the proof, how we would generate the proof theory. So one way to think about the modeling construction is that we're going to take this and interpret that as a fold or something very similar to a fold. So given some given some truth value domain, right? So that could be, 0 and 1 or true and false, or it could be some quantile, or it could be, a probability distribution. So like, the numbers between 0 and 1. So then we want to be able to have this return, this expression here needs to return a truth value of some kind. And so the idea is that we need three ingredients, right? One ingredient is we're going to use when we hit kind of bottom, when we can no longer unpack M and we can no longer unpack this, right? So M is ground in some way and this is ground in some way. Then we need to be able to turn those states. So for example, if M is the 0 process and this is the 0 logical formula, right? Then we're at the bottom and we can't unpack any further. No more recursion. And so then what we need is to provide a truth value for those ground things. So this first argument, F, which is of this type here, is going to provide the truth value for the, when we hit bottom. And then and then we need our term and our predicate, and then we need some initial truth value. So this is our accumulator, right? So just like a usual fold, right? So an F, and an initial pair, which is the term and predicate, and then an accumulator for the truth value. And given those three things, we're going to return a truth value. So for example, we want to take an expression like this, right? So P par Q models phi par C, right? So this is a type, this is a term, and we want to get down to a truth value. And again, the whole point of the collection semantics is that it allows us to consider a wider range of truth values than just true and false. So obviously when we unpack this, because this operator is commutative, when we recursively descend, we want to consider the case where P models phi and Q models C, that's this one, and also the case where P models C and Q models phi, right? So that's this one. And then we have to find a way to accumulate over these possible interpretations, right? So there are two different ways to unpack to recursively descend, so that we have to get we have to get a truth value out of this and a truth value out of this, right? And a truth value out of this and a truth value out of this, right? So this pair is going to yield a truth value. So that's this one, right? So we have to accumulate those two. And then we have to say for the two different interpretations, we need to accumulate those. Does that make sense?
Yes. And why do we need on the type level that par is commutative?
Because it is commutative. I mean, those equations are true, and it will be, and whatever equations hold at the term level need to hold at the type level.
I see. Yeah, first I was thinking that we are saying what is the type of P and what is the type of Q. But we also need to say what are there in par, right?
We have to say what is the type of P par Q. That's a term, right? Right. And we're not really saying what is the type. We're asking whether the type of P par Q is phi par C. Right? Is P par Q a witness of this property?
And they don't have to be the same. So I'm thinking
what is they, and what do you mean by the same?
P and Q.
P and Q can be completely different processes.
Yeah, I'm thinking how to satisfy if they change positions, how they will satisfy.
Again, you don't know. I mean, you don't know that the entity or agent that wrote down this type was aware that you wrote P par Q this way, right? They wrote it this way, knowing that this is commutative. So they don't really know what order this instance came in. So you have to check all possibilities. And then you have to accumulate them. Right? So here, this accumulator, right, has to be polymorphic, right? This accumulator has to come from the truth value domain. The truth value domain is like a monad plus. Does that make sense?
Yes. I'm thinking we are basically extending all possible combinations. I'm thinking about the whole tuple space where we have lots of processes in par. They can be described also.
Yes. So the tuple space is going to be something like this, right? And then we can demand that the tuple space is going to be a big parallel composition, right? And we know that parallel composition is completely inert. So just to be super clear about this, the tuple space always looks like, let's see how this works. No, hang on a second.
Does this mean that computing types, complexity of computing more pairs are not linear?
It is not linear. No, it's terrible. The complexity gets worse and worse. But notice that you couldn't write this down previously, right? Yes, the complexity gets bad, but at least we can write something down.
Yeah.
Okay. So all right. So we have. So really, I'm going to call this P. In and P out. This way. And then this is I, and this is J. All right, so this is okay. Right, so the tuple space is a process that looks like this, and we know that the integrity constraint on the tuple space is that there's nothing in here that interacts with anything in here. Does that make sense?
Yeah, of course.
Okay, so then the one thing that we know about tuple spaces is that fact. And so what we can say is this is the integrity constraint for the tuple space. Right? Yeah, like there is no way to evolve to another process. So this can't happen. So this is always true of the tuple space. Right? Right. So that's so you can now start to see how the behavioral types have real value, right? We just wrote down in a single line the integrity constraint that we maintain for tuple spaces.
Yeah. That's nice.
Cool. But the point here is that the point here is that this isn't just about processes, right? These are any terms that we can, for which are terms in some rewrite system, right? So this signature is completely generic, right? It's parametric in M, it's parametric in phi, right? And this is what's necessary to do the models construction. And this is just an example of how this signature, what we demand here in order to do models is, it works for the Rowlang row calculus situation, but it works for others. Now, by the way, the spatial logic model checker is cleverer than this. What it does is it orders these into streams. So you can think of it as kind of halfway to prologue, so that it explores, it's trying to negate as fast as possible, right? So it explores, because that'll stop the computation, right?
But if we want to get to the true at the end, we need to explore the whole tree.
Correct, exactly. But it orders them into streams, right? And then it moves through the streams looking for a negation so it can stop.
Mhm.
Yeah.
And you're using fold, but this is not really necessary. I mean, fold somehow implies that this is sequential, but this is not really necessary, right? Or it is.
Well, the term structure has a partial order to it. There's no question about that, right? The term structure always looks like a tree, and a tree is a partial order.
And we can basically use this to split in parallel chunks if we like, right?
Correct.
To do the fold.
That's right. Okay, so that gives you the model theoretic side. Someone needs to mute. Someone needs to mute. Thank you. Okay, so now let's go over what's going to happen on the proof theoretic side. Right? So remember, we said there are two possible interpretations for typing, and we've gone over what happens for the model theoretic side. Now, where are we going to get the proof rules? And so it turns out that the proof rules are given quite straightforwardly. For every alternative in the term language, you're going to get proof rules. The alternatives that that only mention non-terminals are going to be proof rules with no hypotheses. Right. So without anything, we can conclude one. And then what we want to do is conclude that one is of type 1, right? So essentially, for every alternative, we're going to get introduction and elimination rules. And the non-terminals will be introduction rules that give the corresponding types here. But these, where you have non-terminals as opposed to terminals, they will have hypotheses, right? So the hypotheses will be that you can prove that M of X is of a given type, and M of X is of a given type, and then you can prove that the combined thing is of the combined type, right? So these are going to give you introduction and elimination rules, and then you proceed by so given a term, you're going to unpack the term and unpack the type walking backwards, right? So that's how you'll do the proof theoretic approach. So that gives us I haven't spelled out the algorithm. I'm just giving you the intuitions as to how that works. But it's straightforward, right? There's not a lot of magic here. It's more complicated when we're not just considering this structure, but we're also considering the modal stuff. But Mike developed a trick some while ago, like a couple of years ago, where we encode the theory of a graph in by we take a syntax like this, we transform it to a new syntax where we've got source and target constructors. And then the rewrite rules are whoa, what happened there? And then the rewrite rules are the arrows built from the source and the target. And so then you can apply all the same tricks that we're doing here syntactically to the rewrite rules. So just when you've got a source and a target as a part of your term, and so you can do the modal operators in terms of source and target, and you have certain equations on source and target that are clear. So that then simplifies the modal rules so that they follow exactly the same procedure. nothing magical. So that now tells you the whole shape of the algorithm, right? So what we've said is now the one thing that's tricky with respect to the proof rules here is we haven't said what it means for proof rules to work over different truth values. So that's an area of research that we still have to work on. Certainly for when the truth values are true and false, it's very clear. But when the truth values are more sophisticated or nuanced, then we have to say what that means in terms of the operations of the proof rules. So very likely we'll do the same trick that we're doing here where we have an accumulator, right? So the proof rules will keep a truth value off to the side, right? Which is then accumulated as you move through the tree. So that's the proposed avenue of investigation.
So this is in a sense, if we have some kind of range instead of true false. So we are accumulating all of the whatever we whatever we accumulated, and then we decide at the end. Right?
Yeah.
Exactly. And you mentioned that something in the in these constructors. I'm not sure, but is there some kind of condition that when you were describing Abramsky's representation? So
oh yeah, that's right. That's right. So it turns out that there's a simple way to do that by moving to Lever's theories with infinite sorts. So which I believe still works. So at least for Abramsky's thing for linear terms, you can write them down in terms of higher order algebraic theories, which is an extension of Lever theories to include binders. Right. So higher order algebraic theories where you've got a lot of sorts, and then for each different sort, which is each different sort is going to correspond to how many variables you've got, or the variable sets basically. And now you can code up the constraints using the different sorts. So that's something we have to write down, but Mike is fairly confident that approach works to encode the linear constraints at the type level for this representation of Abramsky's terms for intuitionistic linear logic.
And how this is and how is this represented in the proof theoretic representation when we have hypothesis and
so what will happen is again, you'll have introduction rules and elimination rules that mention specific sorts. So right, so those will get particularly large and possibly unwieldy because you'll have infinitely many of them, but they'll all have the same shape. Yeah.
I see.
Yeah. Okay, that's all I had to cover today. But I think this is good, right? Because now we're down to brass tacks, right? I'm talking about how to implement Ladle for in a relatively straightforward way, where we can contemplate a Scala implementation that takes on the order of a couple of months. So we've given the semantics, we've given the syntax, we've allowed it to work over a range of containers and a range of different truth values. And there's still some interesting gadgets, right? So for example, oh, that wasn't the one. Is it this one? For example, we want to spell out, we want to be able to spell out structures like this, which give us notions of negation. So that's right here, we've been in a presentation like this for lists, we've been very, very careful to be explicit about the interior structure of the list. Whereas here, we haven't said anything about the interior structure of set. What we've said is that we've given an algebraic characterization rather than kind of an implementation. And so we want to be able to bridge these two worlds, and something like this at least gives us a notion of negation for a wide range of containers. So still have some work to do in terms of being able to flip back and forth between the kind of like the term level view of the collection and the algebraic view of the collection. So still sort of some issues there that we want to think about, but in general, I think this is crisp enough that we can begin an implementation, and the implementation can benefit as we work out some of these additional questions. Any other questions or comments? All right. Thanks very much. I will see many of you in the dev stand-up.